All right. I have the camera set up a bit better this time so that we're closer to eye level. I don't have these lamps glaring anymore. I'm just filming during the day with the lights open. Uh, and hopefully you're a bit closer to the board so you can see more of the board, but I'll be cut off a bit more. But you don't care about seeing me. But in this, chapter 5, this is moving from triangle congruency to triangle anatomy, if you will. So, like lines and circles inside, outside of triangles, and the relationship with those. And we're going to start with this topic, and I suggest you split this into two parts. This first part, which I'm going to tell you about in a second, centroid, incenter, circumcenter, and orthocenter, and the rest of the chapter, which is the mid-segment theorem, the inequality theorem, and the hinge theorem. But going back to what I'm going to talk about here in a second, this part took me 2 or 3 days to memorize and understand fully. And orthocenter, I'll talk about that later, but I still don't quite understand that, and it doesn't seem like anyone else does either. But with that, we're going to cover again 4 concepts of the triangle anatomy. And starting out with the incenter, circumcenter, orthocenter, and centroid. I think I left my markers up back here, yeah. So we'll start with what I think is the easiest to understand is the centroid. And the centroid is the center of a triangle. I don't know if it's an I or a Y there. It might be a Y. I think it's a Y, yeah. Triangle. So if we had our triangle here, right triangle, the best triangle, the center would be somewhere about there, but we're going to prove this using the centroid. And to find the centroid, to prove it, you will take a line that connects the vertice to the midpoint of a triangle. Vertice to a midpoint on any side of the triangle. So what that would look like, and I'm just going to do a quick demonstration here. We'll get into all of them in a minute. That would look like this vertice here to the opposite midpoint. We'll say the midpoint's there. This vertice, a line connecting those, like that. So that is the centroid. Next, we'll talk about the incenter. The incenter is the center of a circle inside of a triangle. So what that would look like is if we had, again, our triangle here, we'll do an acute triangle this time, and then we drew a circle inside of it that touches all 3 sides. We want to be able to find the center of this circle about right there. And to find that, you will take the angle bisectors. So it is found with angle angle bisectors. And the angle bisectors will take is a line coming out of a vertex, out of an angle, that cuts this into two congruent angles. So it cuts it perfectly in half. Same thing like that, cuts it perfectly in half. So that is the incenter. And then similarly to the incenter, we have the circumcenter. Circumcenter. And the circumcenter is the center of a circle around the outside of a triangle. So it's just the opposite of the incenter. The incenter was a circle inside the triangle. Now this is a circle outside the triangle. And to find the circumcenter, you use perpendicular bisectors. So a perpendicular bisector would be, well, found with, I didn't know how to spell triangle. Imagine how I spelled perpendicular. D-I-C-U-L-E-R. I think that's probably wrong, but I've said it several times before. This is geometry, not English. So a perpendicular bisector, if you put the two words together, perpendicular and bisector, would be a line that, if we say this is the midpoint, it's a line that cuts this perfectly in half, and it crosses at a right angle. So it's perpendicular, and it makes these sides congruent. So it would be a line like that. Is a perpendicular bisector. And then finally is the orthocenter. And I've done a lot of working with the orthocenter, but and maybe because I haven't taken geometry yet when I'm making this, but maybe when I take geometry, they explain it better than online or YouTube. But from what I've seen, like I've done a lot of looking, from what I've seen, it's either some weird, complicated explanation, or they say it really doesn't mean anything. It doesn't find the center of anything, stuff like that. But the orthocenter, I mean, again, I don't have a definition, but Ohio State says you need to know what the orthocenter is, so you gotta learn it. And the orthocenter is found with altitudes. With altitudes. And the altitude, it goes from one vertice and crosses the opposite side at a perpendicular angle. Right, so if we have, again, let's not do a right triangle for this one. A right triangle doesn't do it very well because two of the sides are already altitudes. If we do an acute triangle here, like this, and we want to go from this vertex here, we come straight out and hit this perpendicularly at a 90-degree angle, but it doesn't necessarily have to be at the center or at the midpoint or anything, just perpendicular, like that. And now with that, I will show you how to put all of this stuff together. And we will start with, there are three kinds of triangles: right, acute, obtuse. So I will show you how to do everything on each kind of those triangles. And we're going to start with the, we'll just start back up with the centroid. So we're going to start here with the right triangle. Draw a right triangle right here, like this. And let me get a different color. The centroid just tries to find the center of the triangle. I would also like to say that I'm not using a ruler and a compass and everything. I'm just kind of freehanding this. So it won't be exact, but it'll be close. And you can find good videos out there of people doing this with a ruler and a compass, and they find the perfect center of everything. But I don't have that, so mine will be close but not exact. So first I want to label all of the midpoints, because remember, it's a line from vertice to the midpoint. So let's say that's about the middle right there. We'll say that's about the middle right there. And that's about the middle right there. Now, if we go from a vertice and we take this line straight out to the midpoint like that, I would also like to label these so that we are clear that these are congruent with each other because those are midpoints. Then we would go from here to that midpoint and from here to that midpoint like that. And where all of these intersect at, that point where all three lines cross, is going to be the centroid, or the center of this triangle, like that. And if I erase all of these lines here, it will look, kind of like the center of that triangle, because it is the center of the triangle like that. And like if I cut this out of a piece of cardstock or something, that's the point that it would balance on your finger too. Next, we'll go to doing the centroid with an acute triangle. All right, so if we take our acute triangle, like that. Again, if we label all of our midpoints here, I'd say that's right about, it's probably right about there actually. Right about there and there. And if I come out of the vertice and make a straight line to this midpoint, again, that's going to cut that perfectly in half. Then I'm going to take a straight line here to that midpoint, and it cuts that perfectly in half. Then I take a straight line here from this vertice down to that midpoint, and it cuts this perfectly in half. And right there, that point where all three of them intersect is going to be your centroid of the acute triangle, like that. And again, if I erase all of these really quickly, you can see that looks about like the center of the triangle. And finally, the obtuse triangle. I'm terrible at drawing these, but I'll try. So if we make our base, and then right there, something like that. And I take out and label our midpoints. We'll say that's right about there. We'll say this one's like here and here-ish. And I take a line straight out from the vertice to the opposite midpoint, like that, and it cuts this side perfectly in half. I do the same here from this vertice to that midpoint, and it cuts this side perfectly in half. And then one more time from this vertice down, to that midpoint. I had to kind of curve my line there a bit, but I messed up, and it cuts that perfectly in half. And again, that point where all three intersect, right there is your centroid, the center of your triangle. Again, dog chewed up my whiteboard eraser today. Got in here somehow. So I'm using chalkboard eraser because I have a chalkboard on that other wall, and it doesn't work quite as well. But regardless, there is the centroid and the center of the triangle. And I suggest you go through and do those on your own too a couple times when trying to memorize all of this. Next, we'll go to the incenter. And the incenter is a circle inside of your triangle. So we'll do a right triangle like this. And I have to draw a circle. The circle's not going to be a perfect circle, but get close. Kind of. And then I take this, and remember this is the incenter is all three of the angle bisectors, right? So if I take a line straight out of an angle, and we want to cut this angle perfectly in half. So straight out like that, and it hits wherever, and then it cuts this into two congruent angles. Then I take one straight out of here, cuts this into two congruent angles. So those angles will be 45 degrees because it's 90. Then I take one more out of this vertice, straight down, and I cut this into two congruent angles like that. Let me put two on there. Those are congruent like that. And that point where they all intersect is not the center of that circle, but I think I have, if I fix this right here, that got a little lopsided. If I adjust that a little bit, it's kind of closer. And again, if I had done this with a compass and a ruler, it would be perfectly in the center of that circle, but you know, it's okay. So that's for a right triangle. Next, for an acute triangle, we have it like this. I'm trying to draw closer to Bob Ross over there, because I don't know what the camera looks like, but I know it sees more that way than over here. And if I scribe this circle inside here, touching all three edges, it's tangent to all three edges. You'll learn more about in chapter 6, I believe, tangent lines. No, chapter 10 is tangent, I think, I don't know. But I digress. Again, we want to come perfectly out of this angle, cutting it in half and straight, and it cuts it into two congruent angles. Same thing here, straight out, cutting it into two congruent angles, like that. And again, two congruent angles, like that. That was drawn incorrectly. Those definitely aren't congruent, but regardless, this point right here where they all intersect is going to be the center of your circle. And again, it's not perfect, but I'm doing it freehand. But that's how you find the incenter for an acute triangle. And finally, an obtuse triangle. So I take it like that. And that. Okay, and if we again draw our circle inside, Hopefully this feels redundant by now. It's a good thing. Circle would be about there. And I know that's more oval, but... And then we come straight out of this angle, like that. Cuts it perfectly in half, two congruent sides, because it's an angle bisector. Again, straight out like that, cutting it into two congruent angles, because angle bisector. One more time, like that. And that point there where they all cross is the center of the circle. I think that's the best one yet. So there you go. That's how you would find the center of a circle inscribed inside of a triangle, which, I mean, you're never going to use that except for your geometry OST, and then you can forget all of this. But, I mean, you ask, why should we learn this for our job in the future? Well, it's not your job in the future. Your job right now is passing school, and this will help you pass school. So like that, now we move on to the orthocenter. Not the orthocenter, the circumcenter, I apologize. The circumcenter. And this is where something weird is going to happen. You're going to have three places that they meet. So far they've all met inside, but now they're going to meet inside, on, or outside. So here, if we start again with our 90 triangle, right triangle, like that, there. And we take our circle around the outside so that it touches each of these vertices like that. It's a terrible circle. And now we want to take a line that touches a perpendicular bisector. So it bisects the line into two congruent halves, and it's also perpendicular, right? So if we take this line here, let's first draw our midpoints on these sides so that you know where to draw the line. So first I'd say that's right about there. Then I'd go right here and here like that. And now from here, we can take a line starting here that goes perpendicular straight up like that. So it's 90 degrees, and those are going to be congruent. We also have one that comes straight out 90 degrees right here. And I've done something wrong already, because these are supposed to intersect on, let's say, I draw it out like that, and that, and that, sorry, and again, I apologize for that. I tried to be accurate, and if I did this with a ruler, it would be accurate, but regardless. And we take the same thing out of here, and we want to go both directions with this. And this is also cuts this in half, and this in half, and this in half. Like that. So you can see here, the point where all three of these lines intersect, right there, is the center of the circle on the outside. Right about there. Like that. So that's how you find it, the circumcenter on a right triangle. And notice how that one landed right on the hypotenuse of the triangle. So that would be on the triangle. Now we'll move to our acute triangle here. Like that. And we want the circle around the outside. Something like that. And we want to take, again, a line that goes perpendicular and bisects the side. So let's draw our midpoints here. I'd say that's a midpoint, that's a midpoint, and that's a midpoint. And if I draw the bisectors, so the perpendicular line that bisects that, cuts it perfectly in half and is perpendicular. So something like that. And like that. And that. Again, I judged them incorrectly on the midpoints because it's supposed to meet more around the centroid of the circle. But regardless, you get that point there where they all meet. Draw this in red. And that point there will be the center of this circle around the outside. Oh, sorry, I also forgot to draw the right angle boxes like this. So that would be the center of this red circle around the outside. Like that. So that would be in. So now when we draw the obtuse triangle, it's going to be outside of the triangle, but in the center of the circle. So I take again an obtuse triangle, figure out how to draw this thing. Like that. And I take the red pen, draw a circle around the outside. Something like that. Looks like a lemon, a red lemon. And take the green pen. And again, we want to find the midpoint of each side. So I'll say about here, here, and here-ish. And we take a line that goes perfectly perpendicular, like that, and bisects, so those are congruent, like that. Again, one here, like that bisects and is perpendicular, and one here. I mean, I really messed this one up. I don't know what I did wrong. This one kind of curves, and that's definitely not the center. But regardless, we still did the steps the same. I just have the wrong points on the triangle. With this, the center should be like more around there, because if we twist that, those are all twisted around. But I still think you get the point here, but it should probably be more around there. I mean, again, I apologize for that, but we still did all the steps correctly, and that's really what matters rather than your drawing abilities. And with that, we move on to the orthocenter, which I apologize for not getting you a good definition on this. And if you look it up yourself, they really say it has like no significance of a center of any point of the triangle or a circle that could be inscribed in or around it. Like the others, I've heard it and I don't understand this, but they say it's like if it were raining on the triangle, the orthocenter is the point on the triangle that this would all gather, or like this is where gravity would pull, but I don't know. This is where the gravity generated from the triangle would be, but I don't know. So we'll start here with our right triangle. And remember, this is made up by a line that comes straight out of a vertice and then goes and crosses the other side perpendicularly, right? So if I take out the green, and we want to start, let's start here with this vertex. It goes out of this and crosses this at a perpendicular like that. And that's it. It doesn't bisect the angle or the side or anything like that. Just out of the vertex, perpendicular to the opposite side. Well, then here, the opposite side of this angle would be right here. But because this is a, let me do that in blue. Because this is a right triangle, it already crosses the opposite side at a 90-degree angle. Because if I had continued that out, it would be perpendicular. So, I mean, your green line would be right on top like this and crosses perpendicularly there. And the same thing right here, because if I had extended this out, this crosses this at a perpendicular angle too. So this one is going to be right on top like that. And then the point where all three of these cross is going to be right here on the triangle, right on that 90-degree vertex there of the triangle. So that would be your orthocenter when you're asked to find the orthocenter of a triangle. For a right triangle, it's going to be right on that vertex every time. So that was pretty easy to remember. You don't have to draw out all the steps every time if you know it's a right triangle. Next, for an acute triangle, like that, we want to take a line straight out of this vertex that goes straight down. Well, it doesn't have to go straight down, but it crosses this perpendicularly. Same thing here. Crosses this perpendicular. And here, you cross this perpendicular. Just like that. And that point there, where they all cross, is your orthocenter of the acute triangle. Again, really close to the circumcenter. And now the weird one, the obtuse triangle. And you'll see why in just a second. This one always messes people up. There's a reason I put this one last with the obtuse triangle always last. So that we can spend a lot of time on it. If I draw the obtuse triangle, and I mean this first one is going to be easy, right? Just like all the rest, we come straight out of here, we cross this perpendicular, just like that. I'm going to extend it out just a little bit. I extended it more that way than I did the other way, but like that, that would be one line here on this. Well, next, if I want to take this and hit this at a perpendicular angle, well, I can't stay inside the triangle because that wouldn't be perpendicular. So what you have to do is imagine if this side had continued out, then we could take it like this, and then you could come down at a perpendicular angle, right? How that's kind of a right angle there, like that. And then the same thing for this right here, because you can't stay inside the triangle. It wouldn't be perpendicular. So you have to imagine that this is extended way out like this. Then you can take your line to cross this perpendicular, like that. And then this point where they all meet, outside of the triangle, is your orthocenter for an obtuse triangle. So this point way out here is the orthocenter, because you have to extend some lines and imagine stuff's there that isn't there. And I think that's why State of Ohio said you have to know the orthocenter, just because this looks confusing and they want to scare people. No, I don't think that, but all right, now I suggest that if that's the first time you've heard about any of that stuff, go back, watch it a couple times, practice, draw them on your own, do whatever. Before moving on to this next part here about the mid-segment theorem, hinge theorem, and one other theorem. What is it? The inequality theorem. But I'm going to continue on. See if I can film one other video in one whole take, unlike the other two that I just did. Okay, the mid-segment theorem. Ooh. Well, darn. Okay, that just rolled under my desk. I guess we'll be working in orange for the video. Like that marker. Okay. If we have a triangle here, like this, here, like that, there's our acute triangle, and we want to take the mid-segments of this triangle. Well, we've done that a couple times before in our previous orthocenter, circumcenter, whatever that section was called. But if we take the mid-segments, and this time it doesn't have to be quite as exact. I mean, it does have to be exact for the rules to make sense, but there's not going to be anything wrong if I'm off by a centimeter like there was in the last one. So let's say those are our midpoints of these triangles. And what that means is that this side and this side are going to be congruent. This side and this side are going to be congruent. And this side and this side are going to be congruent. Like that. And now from there, we can go and draw a line that connects each mid-segment to the other mid-segments. So if I take this 10 here, like that, and that, we get another small triangle inside of our larger triangle, like that. Like that, yeah. And we know what else we can determine from this is that, let me get the green pen for marking this stuff, is that these opposite sides here, so see how this side and this side are opposite, we know that these sides are going to be parallel to each other, like that. So again, then this side and this side would be parallel, like that, and this side are going to be parallel, like that. Already this is getting pretty complicated, but we're also going to be able to know that these opposite sides, one part of this like small segment here, is also going to be congruent, like that. So then these opposite sides, these are going to be congruent, and these are going to be congruent. So now you have all kinds of scary tick marks all over your shapes. It makes it pretty cluttered, like that. And there's one more thing on here. I forget what it was. Okay, sorry about that. I lost my mind there for a second. I couldn't remember what I was thinking of because I was thinking of something else that had to do with a, a different chapter entirely about the centroid theorem, not the mid-segment theorem. So I apologize for that. But we just went over how these sides are going to be parallel to each other. And let me erase these parallel marks because I'm not going to really talk about them right now. And I mean, it's important to know, but I'm more interested in these tick marks, the lengths. So if we know that one of these sides is always going to be parallel to another side, but it's also going to be half the length of its parallel side, right? So, and then because this is split into two equal parts, then these three are going to be equal. Yeah, same thing here. This is half of this, but because we split it into three parts, these three are going to be equal. And what that entails for us is that if we know the entire length of one side, like we know the length of this is 16 centimeters, then we already know the length of this is 8 centimeters, just half. And same thing, vice versa. We know that if this is 8, this is 16, and then each of these are going to be 8. Like that. And with this, we can do all kinds of algebra and solving for, unknowns, X, Y, Z, whatnot. So, I mean, this theorem's pretty lackadaisical. It's pretty simple, So I'll just give you one example of these, one problem like this. And then we'll move on to inequality theorem next, I believe. So if we have, that's a triangle, then our mid segments are here, here, and back, like that. And we are told, I should take this with me so I'm not walking back and forth, taking more of your time, because this video is already 40 minutes long. More like that. And this entire length here is 3y minus 5. This is z plus 1, and this is z like that. We have to solve for x, y, and z. So, pause, try to figure that out yourself. Think about it for a minute. Okay, let's walk through this first. Okay, I apologize for that again. I know I said we're going to try to do this video without any cuts, and now I've put 2 or 3 in so far, I don't know. But for the practice example on this one, we're just going to do one. Again, I don't know where I'm cutting this, but we're just going to do one example because this is a pretty easy theorem here to learn and memorize. You just have 2 parts to memorize. But here we have 18 is the entire length of this. 4y plus 4 is the entire length of this. And 3y minus 5 is half the length. See, and that's the problem why I had to cut this, because I had this as the entire length and I messed everything up. I should have just rolled with it, but in hindsight's 2020 and whatnot. So you're going to have to solve for me x, y, and z, like this. So if you pause, try to figure that out yourself. I don't know why I erased that. I still need that up here. Okay, so let's start out with the simple stuff with that 18 and z. Well, I know that this length here is half of this length, and half of 18 is 9. So I can just put 9 there, and we know right off the bat that z equals 9. Now from there, we can move to z plus 1 is 10. 9 plus 1, I shouldn't have to explain that. And then we know that 2 times this is going to equal 4y plus 4. So 2 times 10 is 20. So we know 20 equals 4y plus 4, like that. And then from there, we have to subtract 4. We know that 16 equals 4y. And we divide by 4. 16 over 4 equals 4. And we know 4 equals y, like that. And then for x, well, we can plug in here. We know that x equals 3y minus 5, right? So we know x equals, because half of this entire length, this is half of this entire length, and so is x. We know that that is half of that. So we know x equals this, 3y minus 5, like that. So all we have to do here is plug in y. X equals y equals 4. Remember, so 4 times 3 is 12, minus 5 is 7. X equals 7, and we plug that in here, and that's your answer, 749. Like that, and that's all you have to do for this one. Now, moving on to hinge theorem, or inequality theorem. I don't know what I have listed next. Probably inequality theorem. Let's see. 5th page, inequality theorem. So this one is also really easy. This is probably the easiest triangle theorem that I will teach. The inequality theorem means that one side of a triangle can't be greater than the sum of the other two sides. It's the technical term. But really, all that means is that if we have a triangle like this, it means that this side here, we'll call this x, x can't be any larger than these two sides right here. And that's because if we think of a triangle, this is the way that I would think of it. If we think of a triangle as starting as like a 3-sided box like this, and then the other ends fall in until they touch, right? That's how you could think of a triangle. Or at least an acute triangle. For an obtuse, it would be they're both falling. This one falls faster. But to get this point across, what we're trying to work with, if we start with this base just being, 4 units, and then we have our 2 upward facing sides like this. One will be 5. We'll call this 5, and that's 3. And as these both fall inward, do they touch each other, or do they're not long enough to touch and they just keep swinging, right? So as these fall in, if you can picture that visually, you'll see it stops at something like this. So they're going to hit each other at 3 and 5 is 4. But you can also see 3 and 5 is 8, and 8 is larger than 4. Yeah. Next, well, what if we had something? What if our box looked like this? What if we had this was labeled down here? Let's just restart. If this down here is labeled as 10 units, and this here is 6 units, and this here is 4 units, like that. So here, they're going to touch as they swing inward, like this, but they're not going to touch fast enough. They're just going to collapse down into a line again. So it would look like that. They just come down and touch, and they're parallel. They become the same line as this. And if you look, 6 and 4 is 10, and the base is 10. So when you add them together, it's the same length. And that doesn't make a triangle, right? And finally, we have something like this. This is 5 units here, and then we have 2 units and 2 units like that. Well, you can already see that those aren't going to reach. Those aren't going to reach, and they're just going to fall flat. I don't know if you can see. They just fall flat. They never touch each other as they swing down, and you get something that would look like this, and that's not a triangle. And then mathematically, 2 plus 2 equals 4, 4 is less than 5, and it doesn't make a triangle. So that's why the hinge theorem, or not the hinge theorem, the triangle inequality theorem is true. Yeah, and I mean that's not the technical way of defining it, but I think it works just as well. And then from there, I'll move on to, I feel like you don't need an example for that, like, because, I mean, you understand that. And then the hinge theorem says that the longest side always has the largest angle opposite it. Right, so, and what that means is, if we look at the probably not the most common would be like the regular 60-60-60 congruent triangle. But at least my favorite triangle, the right triangle, if we look, we know 2 things about the right triangle already from pre-algebra, and that is that, and even the Pythagoras' theorem, is that the hypotenuse is always the longest side of the triangle, and the right angle is always the largest angle. And look at this. They're opposite each other. So the opposite angle of the hypotenuse is 90 degrees. That's that right angle. And that's really what it states. So again, something that's not so common would be like a triangle like this. And I mean, you can look at it and go, this is obviously the longest side. If we say this is x, 2x, 3x, it's not proportioned out that way, but then we already know that this angle here is going to be greater than any one of those 2 angles there. So something like that. Same thing up there. And that's what the inequality theorem states. But what we can also do with this is ask questions. Well, as already stated, we could ask a question. If I don't draw this to scale, right, so you can't just look and tell. If we say this is 7, 5, and 2, and I tell you, and I ask what's the largest angle, you can look at this. Well, 7 is the largest number, and the angle opposite would be this, so this is going to be the largest angle. But what we can also do with this is, if we have another triangle like that here, 40, 60, 75. We say this is 40. This is 60. And this is 75. Like that? Yeah, that equals 180. And I ask you, what's the longest side of the triangle? Well, you can look and go, well, I mean, 75 is the largest angle, and the side opposite would be this right here. So you could say that this is, that is the largest. Like that. And the reason this is true is because the longer the side is, these other two sides are going to have to swing farther, creating a larger angle than if it were real close like that, if that makes sense. My arm demonstrations. And then from there, I have some examples for you. How many do I have? I just have, one, two, 3, 4, 5. I have 5 examples for you. And then this long, over an hour video will be done. And I apologize for making this so long. I probably should have split this up. I'll probably have to cut chapter 10 in half because chapter 10 is twice the length of this was. But here, if we have a kite-looking shape like this, and I cut this into 2 triangles, yeah, and we say that, you know, these sides are congruent. And then this is 50 degrees right here and 45 degrees right here. Make that longer. Then what side is longer, this side or this side? We also know that this is the same because of that, again, the reflexive property that I love so much. So what side is longer, or are these sides, or are these congruent here? And you would say, well, this side is going to be longer than this side, so these are not going to be congruent, but they're going to be similar. And I think we talk about similar triangles in the next video, but this would be side angle side similarity because this tertiary side is not the same length as this side over here. Like that. Okay. Now onto the practice page. Okay, we have this diamond shape. I refuse to say rhombus. Okay, A, B, C, D. A, B, C, D, like that. And I tell you that these sides are congruent, like that. I tell you this is 38 degrees, and this is, 41 degrees like that. And I apologize if you're watching this and hoping for radian, but you're not really taught radian before geometry. Unlike me, I was taught radian really early, but that was me being stupid. But still here, we also know that those are going to be congruent again. And if I ask you, are these going to be similar or congruent triangles, you can look and go, well, this side is going to be longer than this side because this is a larger angle than this is. And we know that AD is greater than AB, like that. And that would be your answer for this one. So give me a second here to get your next diagram up. Hopefully you can still see these. I'm still fiddling around with this new camera setup here. You know, hopefully it hasn't shifted at all, because it was shifting around when I was messing around with it. But and I will tell you, but I have QRST, PQRST, PQRST, like that. And I ask, is PR, so this right here, or PR, so this right here, which of these two sides is greater? But I apologize, I forgot to tell you the angle measures. This is 62 degrees. That is 67 degrees. No pun intended. I should have changed that. But you can look at this and go, I'm going to put a greater question mark. You can look at this and go that 67, I hate myself, I apologize, is greater than 62, which means that TR is greater than PR, like that. And that would be your answer on that one. Like that. Next. Okay, it wasn't me this time. This time my camera ran out of storage, so I had to fix it. Now, I just have 2 more examples. I'm going to go through these quickly because I've been doing this for 2.5 hours now, and I am not tired of it. Okay. I have this one right here. Like this, and we're going to tell you that those sides are congruent, that this is 82 degrees. And if that's 82 degrees, we know that this angle and this angle are going to be supplementary. So if they are supplementary, this would be, you'd have to subtract 180, this would be 97 degrees. 97 degrees, and then from there I can also tell you that those are going to be congruent, which means that we just have, that we know that these are going to be similar. And 97 or 82, well 97 is larger, so I can tell you right now that this side is going to be larger than this side. And one more example before I finish. We have 2 triangles here. Just give you the 2 triangles this time. We have X, Y, Z like this. And we're going to do that, and this will be, I don't know, 42 degrees. I know it doesn't look like 42 degrees, but, and then here, 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 and we'll have this side, and this will be 48 degrees. And now I ask you, we'll go L, M, N, like that. Now I ask you, which side is larger, X, Y, or L, N? And I couldn't tell you this one because these 2 angles are in different spots and they're measuring 2 different sides, right? So there's no way to tell, and this was more of a trick question than anything. And now, finally with that, that is the end of the first semester of geometry. And you can go to chapter 6, the second semester. Let's see if I flip to chapter 6 here. That is going to be just regular polygons, interior, exterior angles, like that. And that one shouldn't take too long. All right, chapter 6.